Trias white papers. Introduction. The IAS machine, born in the 1950s, represents a new height of human intelligence. Its von Neumann architecture has also become the cornerstone of contemporary information technology. With the past 60 years' rapid advancement, especially with the breakthroughs in cloud computing, big data, IoTs, and AI technologies in last 10 years, IAS will be evolving to its new form, intelligent autonomous systems. The new IAS machine will become an indispensable infrastructure for human society, especially when they are carrying our daily life. Consequently, the crisis in lacking trust to them will seriously affect our society's stability. Trusting machines will become a new fundamental need for humanity in the near future. Building the trustworthy and reliable IAS, trias, will be the ultimate goal of Project Trias. The risks of relying on untrusted machines have become significant. However, for the most of time, we trust the machines by default. Computers and the Internet significantly boost the efficiency of our work. However, untrusted applications can lead to data leaking or tampering. Mobile phones meet our basic daily communication and entertainment needs. However, untrusted mobile apps are illegally collecting our personal data and infringing our personal privacy. Smart medical machines identify pathology, diagnose serious illnesses, and perform surgery with robotic arms. However, untrusted analysis and control procedures will lead to privacy leaking and may even threaten patients' lives. Smart home products play the role of housekeepers, cleaners, chefs, or pets, etc. However, untrusted systems will help intruders to peep or control our lives. Wearables, industrial intelligence, transportation infrastructures, and smart city infrastructures will also be machine-controlled. Untrusted systems will put our society in chaos. Apple's ecosystem sets a good example of implementing relatively trustworthy and reliable hardware and software systems. Apple employs secure hardware to strictly control the bootloading process of its operating system and applications. Apple devices' operating systems are close-sourced and enforced with strict security checks. For third-party developed and maintained applications, Apple enforces a very centralized way to control the kinds of software to run on its platforms. All applications must be certified and tested by the App Store. They are also required to develop in Apple's programming language and implement their strictly controlled APIs. In this way, Apple mandates most critical aspects to provide customers with a secure and closed ecosystem. The centralized controls empower Apple with the capability to govern most details of its ecosystem. But this has also created a superpower who has become the ultimate dictator. Customers could only obey and believe unconditionally that their device's manufacturer, Apple in this case, has no intention to do evil. With the development of the blockchain technologies, the decentralized computation and communication paradigm have raised a wide range of attentions. Particularly, its second generation, represented by the Ethereum, aiming at creating a trustworthy world computer with a decentralized paradigm. With high-level computation redundancy and high-degree algorithmically complexity, consensus protocols ensure a piece of smart contract's correct execution, as it would be arithmetically difficult for attackers to take control of sufficient redundant executing environments and challenge the algorithm's complexity. On the other hand, the smart contracts are open-source scripts and usually only implement very simple semantics. Therefore, their correctness is not difficult to examine. Smart contracts pioneered a way to genuinely execute trustworthy applications. However, implementing general-purpose applications on common computation platforms, such as PCs, mobile, or IoT device, as smart contracts is a non-trivial task. Critical challenges should be considered. Inefficient consensus. Reaching consensus is a high-cost task. POW requires substantial computing powers, which is consumed by inconsequent workloads. Heavy redundancy. Blockchain platform implements undeniable smart contracts operations by enforcing high redundancy. It will result in serious computation waste and network congestion, hence seriously limiting the number of programs to run in parallel. Restrictive interface. Though many smart contracts are Turing-complete, the functional library is far from enough. It will be extremely complex to implement the native application service logic with the existing smart contract APIs. Reconstruction and migration. As a brand new programming paradigm, it would be extremely complex to migrate existing native applications to the smart contract platform. Re-implementing all the existing software on this new platform is laborious, if even possible, given the restrictive interface stated above. Trustworthy data collection. The trustworthiness of the data collection procedure is critical to a blockchain-based system, as it would be meaningless to protect the integrity of tampered data. Human factors should be avoided as much as possible, but untrusted data collection application is also destructive. Data privacy preservation. Blockchain is not designed to preserve privacy. In contrary, it ensures integrity by a high degree of openness. Therefore, enforcing privacy-preserving computation on blockchains is a particular challenging task. Trias's vision is to build a trustworthy and reliable general-purpose computation infrastructure, where any system and software implement only expected behaviors. With Trias, we can root trust into machines with a firm assurance that the machines will deterministically do what they are told to do. Trias builds an all-platform supported native application-compatible smart contract execution platform, development framework and collaborating ecosystem. It has 3 subsystems. Leviatum, a network of trusted execution environments, TEs, to achieve correct executions of general-purpose software. Leviatum implements a heterogeneous consensus graph (HC graph) algorithm, which combines heterogeneous T technologies (TPM, TXT, Intel SGX, ARM TrustZone, etc., and graph computing algorithms, similar to Hashgraph or DAGs. Heterogeneous Ts allow Leviatum to identify misbehaving nodes rapidly while eliminating the dependency on any single technology's provider. E.g. Intel SGX-based consensus requires a strong dependency on Intel's centralized online verification service. Meanwhile, HCgraph's gossip protocol significantly reduces the redundant T verifications, while preserving a scalable and robust web of trust.